All right, so what we want to do now is we want to find the position from the velocity and the time. What does that mean? In other words, if somebody gives us the velocity and they give us the time, we want to find the position. Now, that's all it means, okay? So there's really two situations. The first situation is when the velocity is constant. The second situation when the velocity is not constant. Now, you know how to do this already, I promise you, okay? So here's what I'm saying. So let's say somebody gives you the velocity, 10 meters per second. Let's be positive, right? 10 meters per second. And then let's say you run for 10 seconds. Well, 10 meters per second for 10 seconds is 100 meters, right? Okay, so that's what I mean. You know how to do this, okay? You know how to do that. But let's just do it, let's just do the math, all right? Okay, so we start somewhere, x initial, then we move, and then guess what? We end up somewhere else. Kind of makes sense, right? All right. Now, what's delta x? Remember, distance equals speed times time. So delta x is just velocity times delta t, right? Look at the units. Meters equals meters per second times seconds. Seconds killed, you get meters, right? Distance equals speed times time. All right, so let's substitute. So we have x initial plus v delta t equals x final. All right, well, that's cool. Let's just rewrite it because I feel like it. So x final equals x initial plus v delta t. Okay? All right, and I suppose we're only going in one dimension, right? One direction, so I could put a little x here, I suppose, right? It's a vx, right? Vx, I assume you understood that, but it doesn't hurt to put it. Okay, so x final equals x initial plus v delta t. And again, all it means is you start off somewhere, you move for a certain amount of time, and you end up somewhere else. Good. All right, that makes sense. Okay, now let's graph. So this is the velocity, right, versus time graph, okay? Now, here I have this thing, right, drawn, right, this green thing, okay? So what is, so really I'm asking, what's this on a graph, okay? What's v delta t for this graph? So look at it. What is v delta t? Well, it's just this area, right? It's the area under the curve, right? Here it's 0, but there it is, okay? There it is. So let's do it, all right? So v, for this graph, right? For this graph, v is minus 2 meters per second. And the time is 2 seconds. So the seconds kill and I get minus 4 meters. So what does that mean? What does that mean? It means that the object changed its position, right? Went minus 4 meters. So it went 4 meters in the negative direction. Okay? So v delta, and we already knew that, come on. V delta t is delta x. No kidding. All I'm saying is when you have a velocity versus time graph, this v delta t is the area under the curve, all right? That's all I'm saying, v, right? So this is just the area under the curve. But you got to be careful. I mean, you can't really just say area under the curve. You got to say area under velocity versus time curve, right? You got to specify that. You can't be lazy like me, all right? Okay, so here. So we want to let x initial be 10 meters. So use this thing here and find x final. Well, gee, I already did it. Sorry. Okay, so the first thing you got to do is find, well, not the first, but whatever. You got to find this, right? You got to find v delta t. So v delta t minus 2 times 2. So it's minus 4 meters. So x final equals x initial. Where is 10? 10 meters. Then we want to add that, so we minus 4 meters, and we get 6 meters. That's all. Okay, so all I'm trying to say is, you know, this is a piece of cake, right? When we have constant velocity, it's nice and easy. We like it. All right, we like it. But that's not how usually the world is, you know. So let's do the more difficult case. Let's say we have changing velocity, so it's no longer constant. All right? So changing velocity. Okay, so here's an example. Now that's changing velocity, right? I mean, starts out here, it goes, you know, it's all sorts of crazy things, right? All right, so come on. This thing is still the area under the curve, you know? V delta t is the area under the curve. Now, when we had it like this, it was pretty simple to calculate, right? Just the area of a rectangle. But how are you going to calculate the area under this curve? I mean, that's what computers are for, right? Okay, so how are you going to do it? Well, you took math, you know how to do it. You're going to integrate, right? So I'm just going to show you in gory detail, just in case you haven't had calculus for a while, okay? So here you go. So what you do, you divide this region of time into little pieces, okay? So you divide t final minus t initial into little intervals, right? Okay, so you do that. And then, so you make these each a rectangle. And then what you do, for this rectangle, you assume that the velocity is constant. So for every one of these rectangles, you assume that the velocity is constant. Okay? And then what you do is you just add up all these little rectangles. You add up the area of all these little rectangles. And that's, you know, it's approximately the area under the curve, right? Right? Okay. Now, so basically this is what we're going to do. We're going to say that x final equals x initial. Then we're going to sum, right? We're going to sum. So we're going to sum the vx's, right? But, you know, every v is a little bit different, right? This velocity is different from that one, you know, so we got to, right? So we're going to sum the vx's. So we're going to label it, right? And then multiply it by delta t. Okay, so make sure you understand this. So this is a sum, right? So it's Vx, and we're summing over I. So it's Vx1 delta t plus Vx2 delta t plus Vx3 times delta t, so forth and so on. That's what I mean by that sum. And you have that in math, all right? Okay, now, and again, this is for non-uniform motion. Okay, now you look at this and say, well, come on, Brother Weber, you know, the velocity's not constant here, you know, it's not there, you know, I mean, come on. And, you know, if you're going to add up all these areas of the rectangles, you're kind of missing the boat, right? Now, it's not going to be exact. True? Well, yeah, I know it's not true. So what could you do to make this thing better? How could you improve our accuracy? What could you do to these rectangles or these intervals to make it more accurate? Well, you just make these intervals smaller and smaller and smaller and smaller, right? Okay, so what does that mean? Well, you've all taken calculus, come on. So you're just going to take the limit as delta t goes to 0. And what's a sum when the limit delta t goes to 0? That's an integral. So you have x final equals x initial plus integral v dt. All right? By the way, I'm sure you know this, but if you don't, what does this integral sign look like? Like an S for sum, because that's what an integral is, right? It's a sum. Okay, it's a sum. All right, so that's how you do it, okay? Oh yeah, I got to put my vx there. Okay, so there it is. So that means that the equation, okay, oh yeah, so that's, all right, so this is fine for the velocity being constant. This is the equation if the velocity is not constant. So I mean, this is always going to work, right? Even if the velocity is not, if the velocity is constant, you just pull it out of the integral, and then you just have integral dt, which is just delta t. So this is always true This is only true if the velocity is constant. Now you can do the same argument with velocities and accelerations, you know. All right. So instead of having x, v, you can have v, va, you know, and again this one, right? So you start off with some velocity, you accelerate for a certain amount of time. Guess what? You have a different velocity. So that's what this thing says, okay? All right, so if this is true, then that's true. All right, now, you know, how do you use this formula or this formula? Well, if this velocity is some nice, easy function to integrate, you know, like you learned in calculus, you just do it, right? On the other hand, if it's simple, like to find the area under the curve, like if it's a triangle or a rectangle, you know, they just find the area under the curve. I mean, whatever, you know, whatever works, okay? Whatever works. Okay, so here's an example. All right, so this is velocity versus time, right? Velocity versus time. So we're looking at this, right? We're looking at this, right? So we start off at 0 velocity, and then we go faster and faster and faster. We want to know how far we went, okay? Okay, so you look at that. First of all, is the velocity constant? No! It's 0, then it goes all the way up to, you know, whatever the 12, you know? So the velocity is not constant, right? If the velocity were constant, it would be like this, horizontal line. So the velocity is not constant. So we have to use this, right? We got to use this. Okay, now they tell us here that it says this line is the function velocity equals 4t meters per second, right? This line. How do you know that? Where'd that come from? Well, again, think of what you learned a long time ago. Y equals mx plus b, right? M is the slope, b is the intercept. Well, there is no intercept, so forget it about that. Now, m is the slope, right? So m is the slope. What's the slope of this line? Well, let's see, that's like sort of kind of 12. This is 0, so 12 minus 0 is 0. So it's 12 meters per second, right? The rise or the change in y is 12 meters per second. And the change in time is 3 seconds. 3 seconds, okay? So what is it? It's 4 meters per second squared, right? Because what's the slope of the velocity? It's acceleration, okay? All right, so, okay, so y equals mx. So y is the velocity. So y is the velocity. M is the slope, which is 4 meters per second squared. And what's the x? X is the time, right? Okay, and notice the units, look at the units. Let's look at the units, gotta look at the units. So velocity is in meters per second. The slope is meters per second squared. The time is seconds. So that seconds kills that second. We get a meter per second equals meter per second. All right, so what's the equation of that line then? Right, well, right there. They didn't write units. So the equation of that straight line is velocity equals 4t, right? Velocity equals 4t. Okay, so if we were in class, I'm sorry to keep saying that. If we were in class, I would have the first half of the class calculate this here by actually integrating this. I'd have the second half of the class calculate this by just calculating the area under the curve. But since we're not in class, I'd like you to do it. So do both, all right? Sorry. Okay? So, in other words, what I want you to do first is just calculate the area under this curve. You know, half base times height for a triangle, right? But then, after you do that, put in here, the velocity is 4t. And so integrate that from time equals 0 to time equals 3. So pause your video and please do that. Okay, I assume you've done it. So let's do it. What's the area under the curve? So it's a triangle. So the area of a triangle is half base times height. So we have half. Okay, the base is 3 seconds. Don't forget to write units, 3 seconds. The height is 12 meters. 12 meters. So what's that? Let's see. 2 goes into 12, 6. 6 times 3 is 18, right? Oh, meters per second. I knew something was wrong. All right? So we have 18 meters. Agree? Because seconds kills the seconds. All right. That's the first way. The second way, we just want to do the integral. So it's an integral. So time goes from 0 to 3. And it's 4t times dt, right? 4t dt. And if you want, you can put the 4 outside. And what's the integral of t? T squared over 2. So you get 4 over 2 t squared. And it's from 0 to 3. So that's 4 over 2 is 2. So it's 2t squared from 0 to 3. And that's 2. T squared is 9 minus, and that's 0, so we don't care. So it's still 18 meters. So there you go. You can do it either way, right? Okay, either just calculate the area or just do the integral. All right, let's see. Okay, I told you that we're going to talk a lot about free fall, and I really mean that. Oh yeah, I already did that. Okay, so we did that. All right. I don't care about that. I don't care about that. Well, whatever we can talk about, I guess. So you should be able to go from a position graph to a velocity graph to an acceleration graph. This is the definition of velocity, instantaneous velocity. That's the definition of instantaneous acceleration. You should know those. If you have a velocity versus time graph, you can get the area under the curve, right, by either integration or just calculating the area. So you start somewhere, you move for a certain amount of time, you end up somewhere else. So that constant velocity, like that, and changing velocity, like that. And the same thing with that. Okay. All right. Let's talk about free fall. Now, why do we care so much about free fall? Well, because it's a nice example of constant acceleration. And you just meet it a lot, all right? In the real world, you deal a lot with free fall, so that's why we talk about it a lot. And it's just a nice example of constant acceleration. Okay, so we already talked about this last time. Free fall is when the only important force is gravity, all right? So if I drop this, I'm not high up in the sky, there's no air resistance is negligible, so I can say the only force acting on it is gravity. So that's free fall. This, on the other hand, the air resistance is important, so it's not free fall. Now, I just realized I forgot to bring a tennis ball. Too bad. Well, it's okay. Because usually I'd have a tennis ball and I throw it all over the room. Real shame. What can I throw that's not going to wreck anything? I'll throw this. Okay? All right. So again, that's free fall, right? Now how about this? Oh, gee. How about that? Okay? So once it leaves my hand, and before it hits the ceiling, is that free fall? Or how about this? How about this? Okay, once it leaves my hand, after it hits the wall, is it free fall? Or, how about this? Okay, once it leaves my hand, before it hits the wall, the ceiling, is it free fall? Now, most of the time when I do this, people say, no, it's not. And then I look at them and I say, no, wait a second. I don't care how I throw it. After it leaves my hand, what's the only force acting on it? gravity. So therefore, is it free fall? Yes. All right? So I don't care how I throw it. As soon as I let go, and before it hits something, the only force acting on it is gravity. So it's free fall. All right. Now, I got this from the web. I don't guarantee it's true. I should really figure it out one of these days. But anyway, so this is kind of like the difference between like free fall and non-free fall, So with air resistance is not air resistance. So if you go to the top of the Empire State Building in New York City, which is a very tall building, right? If you have, if you include air resistance, it's a really long fall. So it's not free fall because the air resistance is important when you have really, really long distances. So according to what I found on the web, which I don't necessarily know is true, if you include air resistance, if you drop a penny from the top of the Empire State Building, it will be moving at 25 miles an hour at the bottom. And they claim that's painless if it hits you. I suppose it depends on how it hits you, I don't know. But anyway, if you do it without air resistance, right, which is not a good approximation, it will be moving at 210 miles an hour, which is certainly going to hurt, right? It's going to break the skin. So, all right? So, like again, in the room here, where it's not falling very far, we can ignore air resistance and it's free fall. But if you're outside and you're top of some tall building, you really shouldn't say it's free fall because air resistance is usually important. It depends on what it is, though. All right. Okay. Now here's an important number. So for the Earth, okay, near the surface of the Earth, the acceleration due to gravity in the y direction is minus 9.8 meters per second squared. So again, we're saying positive up, negative down. All right? So this is acceleration due to gravity, minus 9.8 meters per second squared. Now you get sick and tired of writing minus 9.8 meters per second squared, So what you do, you just say that g, which stands for gravity, right? G is 9.8 meters per second squared. Okay? So we're going to do that all the time, all right? But the important thing is, look at g is a positive number, right? G is a positive number. But with this coordinate system, a sub y is minus 9.8, so it's minus g. So sometimes people get confused with those minus signs. So what you have to remember is that g is a positive number. That's all you got to remember. G is a positive number, all right? If you remember that, you'll be fine. Okay, so let's do an example. All right, so let's just pretend that I have a ball and I throw it straight up, okay? And let's say that the initial velocity is 30 meters per second. And let's be totally lazy. So we're going to say that a sub y equals minus 10 meters per second squared. And you'll see why. Just keep the math simple, okay? Now, by the way, remember, a is delta v over delta t. So that's the same thing as saying that the velocity is changing by minus 10 meters per second every second, right? Because meters per second divided by a second is a meter per second squared. So this is actually a really great way to think of it, right? That a, delta v over delta t, minus 10 meters per second every second, all right? All right, so let's do it. I'll make a table here. Let's see. It really needed that big, oh, whatever. So this is the time, and this is the velocity. All right, so initially, I'm saying it's going up at 30 meters per second. Oh yeah, this is in seconds. This is in meters per second, so I don't have to keep writing. Okay, here's the question. It starts off at 30 meters per second. What is the speed after 1 second? Now think about it. This says that the speed is changing by minus 10 meters per second every second. So if we start at 30, what's the speed after 1 second? Well, it's 30 minus 10, right? So it's 20, which would kind of make sense, right? Because it's slowing down, slowing down, slowing down, you know? And again, it's the velocity change by minus 10 every second. Okay, 2 seconds, what's the new velocity? Well, change by 10, so it's 10. 3 seconds, 0. 4 seconds, now careful. So okay, so it's at 3 seconds, it stops. What does it do now? Oh man, it turns around. Agree? It turns around. So now it's going down, so it's minus 10. And then, sorry, then at 5, what is it? Well, it's changing by minus 10 again. So it's minus 20. And then at 6, what is it? Minus 30. Okay? All right. Now, don't forget, we had x final equals x initial plus integral v dt, right? We just did that a couple of minutes ago. Okay, so what I want you to do, please, is use this data and make a velocity versus time graph. All right, and it's helpful if you have graph paper. So use this data and make velocity versus time. So do that, please. So pause your video and do it. All right, I assume you've done it. So there it is, right? We started, time is 0, velocity is 30, then we go 1 second 20, and da 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 da, right? The velocity is 0 at 3 seconds. Velocity is 0 at 3 seconds. What do you notice about the slope? It's constant. Well, no kidding. The slope is constant, minus 10 meters per second squared, right? It's negative slope, right? And it's, right, agree? I mean, you know, look, let's go from here to here. The slope is minus 60 over 6. That's minus 10 meters per second squared, right? Okay, so it all makes sense, you know. Okay, what do we call this point here? Time equals 3 seconds. What's that called? Well, the velocity is 0 and went from positive to negative, so that's the turning point, right? You know the turning point. Okay, now what I want you to do is use this, and now what I want you to do is make a table and find the position. Sorry. All right. So now what I want you to do is find the position. All right. So I guess it's y, right? All right. So find the position. Now we already know. Okay. So find the position, and we're going to say at 0, it was at 0. Okay. So we started off on the floor. All right. So find the position at 1 second. Find the position at 2 seconds, and now don't forget. This is how you do it, right? The final position is the initial position, which is 0, right? So 0 plus, and what is this? It's the area under the curve. So for 1 second, you want to find the area under this curve, right? So, you know, so it's this rectangle plus this triangle, all right? So it's going to take you a while, I know, but, you know, it's important, trust me, okay? So for 2, right? For 2, you'll find the area under this part, right? So this here, right? Right? So it's this rectangle and this triangle, okay? So do that, please. So pause your video and do it. All right. Okay, sorry. Okay, so do that. So put it in a table and then plot it, right? So calculate it and then plot it. All right. Okay, so I'm assuming that you've done it. So, but I'll give you a little help. Well, no, I assume you've done it. Come on. So for this one, so this area would be, so this triangle, right? I mean this rectangle, sorry, this rectangle. So that's 20 times 1, right? So that's 20 meters. And then, right, so the rectangle, okay, so the rectangle, the area of the rectangle is 1 second times 20 meters per second. So it's 1 second times 20 meters per second, which is 20 meters. But then we also have this little triangle, right? Right? Okay, so the area of that triangle is 1/2 base times height. So 1/2, the base is a second, and the height is 10 meters per second. So that's 5 meters. So you add them, you get 25 meters. Okay, let's do the easy one. All right, so okay, so that's 25. At 2 seconds, you should have 40. For 3 seconds, it's easy, right? Just this big triangle, you know. So half. So it's half. Base is 3 seconds. Height is 30 meters per second. So 45, right? That's 45 meters. Because 3 times 30 is 90, half of 90 is 45. And so you get 3 seconds, that's 45. Now, hopefully you remember this from calculus or something. If it's below the axis, this is negative, right? Okay? So, in other words, the area under the curve at 2 seconds is the same as the area under the curve at 4 seconds, because this area is same as that area, but this is positive and that's negative. So this area here, same as that. So for 2 seconds it was 40. At 4 seconds it's also 40. At 5 seconds, this area cancels this area, so we get the same time as 1, right? At 1 it's 25, at 5 is 25. Then 6, this cancels that. We're back to 0, right? Right? Because at 6, I mean, you have to admit, right? This is all negative, this is all positive, so it just cancels, so back to 0. So that's what you get, okay? This is the height versus time, right? Okay, that's all right? So if you throw it up, you know, it takes, how long does it take to get up there? It takes 3 seconds to get down, 3 seconds to get, 3 seconds to get up, 3 seconds to get down. So this is kind of an interesting graph. Look, it takes 1 second to go from 0 to 25. It takes 1 second to go from 25 to 0. It takes 2 seconds to go from 0 to 40. It takes 2 seconds to go from 40 to 0. Also, at any particular height, I don't want to say that yet. Okay, all right, so there's all sorts of symmetries, right? All sorts of symmetries. Yeah. Okay, let's quit.